Hello guys, welcome back to my YouTube channel. In this video, I am going to discuss how to analyze and design a singly reinforced beam as per IS 456 using limit state method. So this video is going to be very interesting video. Who are new in my channel, please subscribe my channel to get this type of video in future. This video I have divided in 3 chapters. Chapters 1, assumptions and theories. So here basically we will know what are the assumptions are considered in IS 456 and what are the theories we need to know to analyze and design a singly reinforced beam. In next chapter we will see how to calculate moment capacity of a given section, and finally in last chapter we will see how to design a beam section for a given moment. So these are the 3 chapters we are going to discuss in this video. So now let's see what are the assumptions are there in IS 456. So if you go into the clause number 38, you will see there are some assumptions for limit state method. So these are the assumptions I am gonna discuss here. So assumptions 1, plane section normal to the axis remain plane after bending. What does mean it? To understand this, imagine there is a simply supported beam and we have applied a vertical load on it. So beam will bend like this, and at the midpoint we will get the maximum sagging moment, right? Sagging moment mean we will get compression at top fiber and we will get tension at bottom fiber. And here you can see this is the neutral axis. So neutral axis mean it is the axis. If we consider a element within this axis, we will see there is no compression and no tension, but above the neutral axis always there will be compression, and below the neutral axis always there will be tension. So this is the basic fundamental thing. I think all of you know this. So now if we consider a section like this, so this section which is perpendicular to the neutral axis and also perpendicular to the longitudinal axis of this beam, and this section will remain plane after bending. So after bending it will not be like this, or it will be not be like this. Plane of this section will remain same before bending and after bending. So generally we make these assumptions because if we consider that the section will not be plane after bendings, that time what will happen? That time our theory will be more complex. So to avoid the complexity in our theory, we are just assuming that the section which we are considering before bending, the plane of that section will remain plane after bending. So that's why we are considering these assumptions. Now moving to the next assumptions. The next assumptions is that concrete will have a maximum strain value that is 0.0035 in bending. So this is the maximum strain value we are considering for concrete. So this is the maximum strain value we are considering for concrete material, and this strain value will be maximum at the outermost compression fiber. So why we will get a maximum strain value at outermost compression fiber? So look at this beam section. So this is a beam, and if we draw the strain diagram of this beam, it will be like this. We will see there is a linear variation of strain, and we are getting the maximum strain value at the extreme fiber. So how we can say the strain diagram will be linear? Okay, I can prove it. So from elastic theory we know that F by Y is equal to E by R, where F is the stress, Y is the distance of the element from neutral axis, and E is the Young modulus, and R is the radius of curvature. And now if we rearrange this equation, so we can write epsilon equal to F by E, you know that is equal to Y by R. So we can say epsilon is proportional to Y because R is constant. For a given moment the radius of curvature is constant, right? So only the variable is y. Y is nothing but the distance of the element. So now if we consider a element which is the extreme fiber, this time the y value will be higher, and also we will get the higher strain value. So from this equation it is clear that strain diagram will be linear, and we will get the maximum strain value at the outermost fiber. So that's why at the outermost fiber we are considering the maximum strain value, that is 0.0035. And now if we see the third assumptions, there we will see what is the maximum strain value for steel. So we are assuming Fy by 1.15 ES plus 0.002. This is the maximum strain value for steel. So why this value is like this? Actually this is taken from 0.2% proof stress. So here you can see Fy by 1.15, this is nothing but the stress, and here 1.15 is the partial safety factor, right? So if I divide Fy by ES, so basically we are getting the yield strain of steel. And now we are increasing the strain value like 0.002 because we are considering the strain beyond yield limit. So that's why we are adding this value, and this value is coming from 0.2% proof stress. So that's why we are adding it. So this is the maximum strain we are considering for steel. In other country code like ACI code, you can see this is the minimum strain value, but in case of Indian code we are considering this is the maximum strain value. This is not the minimum, this is the maximum strain value. So we are assuming that if we increase the strain value more than this, the steel will totally fail. So this is our assumption, right? So this is what we are assuming here. So if we draw the strain diagram, it will be like this. Here we will get the concrete maximum strain, and here means at the level of steel, it not at the extreme fiber concrete edge. Okay, so this strain value we are getting where the steel is situated. So steel is situated here, right? So in this level we are getting this strain value. And now look into the fourth assumptions. So in fourth assumptions, code have said that you can take parabola, rectangle or trapezoidal as a stress block for concrete. Code have provided parabola as a stress block for concrete, but if you want, if you can take rectangle and trapezoid as a stress block if you have a substantial experimental data. So code have provided you this type of parabolic curve of stress strain diagram, and here you can see this is the maximum strain value, that is FCK, and first we are dividing this 1.5. so this factor of safety is divided because there is a safe factor is there. So all of you know there is a safe factor effect, so that's why basically we are dividing this value 1.5. and also that concrete is a mix of water, cement and fine aggregate and coarse aggregate. So and sometimes we make the concrete in field, right? So if there is any mistake in the proportion, so we may not get that much strength of the concrete, right? So that's why this factor of safety we are dividing, so that we can have a safer side. If somehow there is any error in the mixed proportion, so we can at least we can have the least the strength of the concrete. So that's why we are dividing this factor of safety, and again we are dividing this value another partial safety factor, that is also 1.5. so finally if we divided this value with 1.5, we'll get 0.446 FCK. So it's mean we are only using almost 45% strength of concrete, we are not using 55% strength of concrete. Okay, and here one more thing you need to keep in mind, so that is here you can see the when the concrete strain will reach to 0.002, it will reach to the maximum stress value. Below 0.002 the concrete stress is not like FCK, or if you say 0.4466 FCK, whatever it is. And but be above this strain, the concrete stress value will be constant. So this is the another thing you need to keep in mind. And now I'm going to the next assumptions, that is the tensile strength of the concrete is ignored. It's mean we will consider the only compressive strength of the concrete, that's mean in this zone, the concrete situated in the compression zone, and the concrete situated in the tension zone we are not gonna consider this. Okay, now going to the next assumptions. The next assumptions is the stress diagram for steel, and in case of steel also we are using a partial safety factor, that is 1.15. so you can see here the partial safety factor is very less. In case of concrete we are using 1.5, but in case of steel we are using 1.15, right? So it's, you can, if you ask me the reason why it is, I can say since we are making steel in factory, so that's why, you know, the quality of the steel or the strength of the steel will not that much differ. So that's why we are keeping the factor of safety here less. And if we look into the stress strain diagram of a cold work deform bar, we will see that the stress strain is linear up to 0.8 fy. After that it become parabolic, and after certain value it become constant. So up to 0.8 fy, in this portion the stress is proportional to strain. It's mean if you know the strain value you can easily calculate the stress value, but beyond this stress limit it will reach, here the stress strain diagram will not be a linear, it will be in curve in nature. And here we are using factor of safety 1.15, so it will be like 0.87 fy. And here you can see the proof step, here you can see the proof stage has been used to find out what will be the yield strength of this cold deform bar, because the yield stress point is not well defined. So that's why at 0.002 strain level a line is drawn which is parallel to this portion and it is cutting at this point. So this is considering as the yield stress value for this steel. So this is how we are getting the maximum stress value of this steel. And if you look into the SP16, there is a table A. There you will see after 0.8 fy what will be the stress strain value that is given here. So using this table we can calculate the stress and strain value. Actually this is required in doubly reinforced beam design. In singly reinforced beam design it will not be required. And here you can see the inelastic strain value also given. Inelastic strain mean when the stress value reach to the yield stress, after yielding the material will have some permanent deformation. So these are the permanent deformation value we are getting. And now if we look into the stress strain diagram of a mild steel bar, so here we are getting the stress strain diagram linear up to the yield point. So in case of mild steel, the up to yield point the stress is proportional to strain, so there is no complexity. So easily we can calculate the stress value if we know the strain value in case of mild steel. These are the all assumptions which have been considered in IS 456. Now moving to the theories part. So in theories, first we are gonna see what are the stress strain profile of a beam section. So here you can see it is a rectangular beam and we have provided steel at bottom fiber, and if we draw the strain profile it will be like this. So we are getting maximum strain for concrete, that is 0.0035. I already discussed, could have defined the limit. And in case of steel we will get this much amount of maximum strain value. So if concrete and steel both will reach to the maximum strain, this time we will get this type of strain profile. And now if we draw the stress diagram it will be like this. So when concrete strain will reach to the 0.002, then it will have a constant stress value, that is 0.446 FCK, and I have already discussed how 0.446 FCK came. And the total resultant force, I mean the total compressive force that will act at a 0.42 XU distance, and the compressive force value will be like this: 0.36 FCK into B into XU. So since here the curve is parabolic, so that's why we are getting this type of value. In other countries code they have taken it as a rectangular triagram, but in our Indian code we are assuming it is a parabolic. So that's why there is a derivation how this formula is coming and how this distance is coming. So if you want to know, I can make another video on that topic, so please leave a comment, so that if I get 5 number of comment about this, I will make another video on that topic. This is how we are getting total compressive force. And now if I want to calculate what will be the total tensile force, so that we can calculate stress into area. So here 0.87 Fy, this is the stress value. Here 0.87 is the partial safety factor, and if I just multiply AST, we will get the tensile force value. So these are the stress strain profile of a beam section. Now I am moving to the next topic. Now let's see what are the different type of beam sections are there. So first one is the balance section. So from this diagram you can see the whatever diagram I have drawn, the concrete and steel both have reached to the maximum strain value, just we have just discussed, right? So in case of balance section, our assumption is that concrete and steel both will reach to the maximum strain simultaneously. So if this thing occurred, then we will call this section is a balance section. And if we draw the neutral axis for this section, so here you can see this is the neutral axis for this balance section beam. Now there another case may happen, like when the steel will reach to the maximum strain value, concrete will not reach to the maximum strain value. So that type of section is called under reinforced section. So from this diagram it is very clear that steel have reached to the maximum strain value, but concrete have not reached to the maximum strain value. So this type of section we will call under reinforced section. And if we draw the neutral axis, and you will see the depth of neutral axis for this under reinforced section, which is less than the depth of the neutral axis of balance section. And there is another case, I mean when concrete will reach to the maximum strain value, but steel will not reach to the maximum strain value. It means steel strain value will be the less than of the maximum strain value of steel. And here you can see concrete have reached to the maximum strain value, that time steel does not reach to the maximum strain value. And if we draw the neutral axis for this type of section, so we will see the depth of neutral axis which is greater than the neutral axis depth of balance section. From this diagram it is very clear. So this type of section generally we call over reinforced section. So whatever I have just said, this is all about theory. Theoretically, when we will call a section balance section, under reinforced section and over reinforced section. Now we need to understand what is the practical implementation of this type of section. What is the practical interpretation of this theory? So also you need to know that. So now I'm gonna tell that thing. So first one is the balance section. Balance section mean concrete and steel both will reach to the maximum strain simultaneously. And now if I want to design a balance section, what I need to do, I need to provide exact AST. I mean from our calculation for a given section of beam, whatever AST you will have, I mean you will calculate that AST, you need to provide exact that amount. Like suppose you got 609.45 millimeter square. So practically you cannot provide 609.45 millimeter square AST. Because what will happen in a in in market, whatever the diameter of the bar is available, that is 10 mm, 12 mm, 16 mm, like that. So using them, you cannot match the number like 609.45, you cannot match. So that's why either you have to provide more than that value or less than that value, right? So when you will not provide exact AST, your section will not be balanced section anymore. So that's why practically it's not possible to design a balance section, but if you able to design a balance section, that will be most economical section. So that is only theoretically, but in practically you cannot achieve that. So now you have two options. One is under reinforced section and the second one is over reinforced section. So the question is which type of section you will choose, under reinforced or over reinforced. So let's see. So in case of under reinforced section, what happened? Concrete will not reach to the maximum strength. It's mean we will not see any crack in the compression side when the beam will fail, right? We will obviously see crack in the bottom side, because the concrete will have huge deformation when it will reach this much amount of strain value, right? So the probability of the beam failure will be kind of ductile, because since steel reaching to the maximum strain value, you are seeing the huge deformation, but you will not see that the beam will suddenly collapse like that. So in this diagram you can see, due to this load, we are just seeing some crack at the bottom face. So this is kind of ductile failure. So the probability of the beam, the sudden collapse, is very less. So that's why under reinforced beam is very preferable, because what happened in under reinforced beam, first steel will reach to the maximum strength, then concrete will reach to the maximum strength. So that's why the probability of the crack in the compression side is less. So that's why we generally prefer this type of beam section, and it will show the ductile failure of the beam. And now if we think about the over reinforced section, in over reinforced section what will happen? Concrete will reach to the maximum strength first, then steel will reach to the maximum strength. So initially, when the beam will fail, we will see the crack in the compression side. As per this image, you can see at the design load, the beam will show some crack in the compression side. So if it happen, and further increase the load, you will see the sudden collapse in the beam. So it will be kind of a brittle failure. So that's why we ignore over reinforced section. That's why engineers always prefer under reinforced section, so that the nature of the beam fail become a ductile failure. Because if the failure mechanism of the beam is a ductile failure, then user will get sufficient warning and sufficient time from get out from that building or to repair that particular structural member. So that's why we generally prefer under reinforced section, and it is most favorable choice for us, and that's why generally we choose under reinforced section. As you can see, that video is becoming very lengthy, so I'm gonna cover rest of the part in the next video. So thank you for the watching. Please like this video and share to your friend if you find this video is very helpful for you, and subscribe my channel. Thank you.